Hi, I'm Omkar, and I'll be talking about Khovanov homology and cobordisms between split links. This is the first part of my NCNGT talk. All of this is joint work with Adam Levine. Okay, so we will first talk about the Jones polynomial. The Jones polynomial is a link invariant, which is to say that it takes as input a knot or a link and produces as output a polynomial. However, this output is produced in such a way that no matter the form in which you inputted the knot or a link, the resulting output doesn't change as long as it was the same knot or link. So this is what it means to be a link invariant. Now the Khovanov homology is a functorial link invariant that categorifies the Jones polynomial. We will flesh this out a little bit during this slide. What this means is that the Khovanov homology of a link contains at least as much information as the Jones polynomial. In fact, we know that it actually contains more information. And it turns out that you can actually recover the Jones polynomial from the Khovanov homology. So you can take as in, so the Khovanov homology takes as input a link L and produces as output the Khovanov homology of L. Now this is a bi-graded homology group, as opposed to the Jones polynomial, which was simply a polynomial. However, from this bi-graded homology group, you can take the graded Euler characteristic, and upon doing so, you will have recovered the Jones polynomial. So this is why the Khovanov homology, we know, holds at least as much information as the Jones polynomial. In fact, we also know that it holds more information. Okay, what also makes Khovanov homology really interesting is that if you have a cobordism C that goes from a link L on the left to a link L prime on the right, it induces a map between the Khovanov homology groups. That is, you get a map Khovanov of C that goes from the Khovanov homology group of L to the Khovanov homology group of L prime. And this is why we say that the Khovanov homology gives us a categorification of the Jones polynomial, because in, say, the setting of the Jones polynomial, it isn't meaningful to speak about the polynomial between a map between two polynomials. However, we can meaningfully do this in the context of Khovanov homology groups. Okay, so now we'll define a couple things. Just a second. So we say that a link L splits into links L1 and L2 if L1 and L2 can be separated by 3 balls. That is, if we can think of the link L as being described by L1 and L2, where L1 and L2 are entirely separated from each other. Now we have an analogous definition in the setting of cobordisms as well. So if you have a cobordism C1, that is, say, the cobordism in red over here on the top, and you have a cobordism C2, which is the cobordism in blue here below, then you say that C1, you say that, so if you consider the union of these two cobordisms, that is, if you consider C1 union C2 to be a cobordism C, then you say that C splits into C1 and C2 if they can be separated by S2 times a unit interval. That is, if you can entirely separate the red and blue components from each other. So this is the sort of picture that we will have in mind for the rest of the talk. And in particular, we will always speak about two component cobordisms. That is, where we have only two connected components, a red component and a blue component. This is not to say that the things we talk about don't extend similarly to multiple components, but it's just that it would be simpler to speak of only two component cobordisms. And in particular, these cobordisms will also be colored in a similar scheme. That is, one component will always be red and the other component will always be blue. Okay, so it's already known that the Khovanov functor behaves nicely for split links and split cobordisms. That is, if you took a split link, then the Khovanov homology of the split link is determined by the Khovanov homology of the two individual components separately. Similarly, if you looked at the Khovanov map induced by a split cobordism, that is a cobordism like this, then that Khovanov map is determined entirely by the Khovanov map induced by the red part and the Khovanov map induced by the blue part. That is the Khovanov, and this kind of makes sense because if a cobordism is split, then the red and the blue components have nothing to do with each other. So it intuitively makes sense that the Khovanov maps also don't interact with one another. But the setting we will be interested in for the rest of the talk is as follows. So this is the picture we will be looking at. So you have over here a non-split cobordism. That is, we notice that the red and the blue parts are allowed to be linked up in some complicated way over here in the middle. However, we require that the red and the blue parts continue to be split on the end. So on the end, the link on the left side, the red part, is split from the blue part, and on the right side, the red part once again is split from the blue part. So you have a cobordism that travels between split links. However, in the middle, the red and the blue components are allowed to link up in some crazy way. So this is why it's a non-split cobordism that travels between split links. And I should clarify that even though the red and the blue components are allowed to be linked up in some crazy way in the middle, they're not allowed, like they're still disconnected. So it's not like you could have a tube between the red and the blue components. They're still disconnected, but then they're allowed to be linked up in the middle. And we will consider what the Khovanov map induced by such a cobordism is. So in particular, we'll be interested in whether this Khovanov map actually depends on the linking information at all. Okay, so before we discuss what the main theorem is, we should define a couple things. So if you have a link L that comprises of sublinks L1 and L2, and you have a link L prime that is given by L1 prime and L union L2 prime, then we call a cobordism C that goes from L on the left to L prime on the right as partition preserving if C consists of two components, C1 and C2, where C1 goes from L1 to L1 prime and C2 goes from L2 to L2 prime. So maybe this definition sounds a little convoluted, but on the next slide, we will see an example of this in the case that we actually care about. Okay, so we must now define what it means for two partition preserving cobordisms, B and C, that go from links L to L prime. So B and C both start and end at the same link, L and L prime, respectively. We say that these partition preserving cobordisms are partition homotopic if the ith component of B is isotopic well boundary to the ith component of C. That is, if you looked at the cobordisms B and C and you erased all the components except the ith components, then they'll be isotopic, even though B and C need not necessarily be isotopic cobordisms. So this is the picture that illustrates these definitions, and also this is the picture that we will be most interested in because it describes the main theorem of this talk. So on the left-hand side, we have a non-split cobordism that travels between split links. So this is a picture we saw a couple slides ago in which you have a red component that travels from a red link L1 to a red link L1 prime. And you have a blue component of the cobordism that travels from the blue link L2 to the blue link L2 prime. And we note that L1 and L2 are split on the left side. So on the left end, the red and the blue components are split from each other. And similarly, on the rightmost end, L1 prime and L2 prime are split from each other. That is, the red and the blue components are split from each other on the two ends. However, in the middle, they're allowed to be linked up in some complicated way. So we have a non-split cobordism between split links. And on the right-hand side, what we've done is we've just separated the red and the blue components from each other entirely. That is, you first draw out the red component, and then while forgetting the blue component, and you just draw out the blue component below it. So in some sense, this is just a split union of the red component and the blue component. So we notice in particular that the blue components on the left side and the right side pictures are isotopic to each other, and the red components on the left side and the right side are isotopic to each other. So what this tells us is that this cobordism here is partition homotopic to this cobordism here. That is, so if we're calling the cobordism on the left C, where C is given by the union of C1 and C2, then we call the cobordism on the right sep of C, as short for separation of C, because we form this cobordism by entirely separating the red and the blue components from each other. So even though these two cobordisms, C and sep of C, may not be isotopic, because C is allowed to be linked up in the middle, whereas sep of C has no such linking information. Despite these not being isotopic cobordisms, our main theorem says that the Khovanov maps induced by them are homotopic. So our main theorem is, so now we state the main theorem in slightly technical language using the definitions we used before, but the main picture that captures this theorem is the one we just discussed. So suppose you have two cobordisms B and C that go from links L to L prime, and these cobordisms are partition homotopic cobordisms traveling between split links. Then the induced Khovanov maps are homotopic to one another up to an overall sign. So in this picture, we suppress the overall sign just for the sake of keeping things slightly simple, but technically there is an overall sign over here. Okay, so now we'll discuss a few applications of the main theorem. And the primary application is that we can separate out any closed cobordisms. So what do we mean by this? So Barnatan wrote a paper on Khovanov homology where he introduced some sphere and torus relations. And these tell us what kinds of Khovanov maps are induced by a sphere and torus in three-dimensional space. That is, what is a Khovanov map induced by an unknotted sphere and an unknotted torus in three space? So on the left-hand side are the sphere and torus relations that were introduced by Barnatan. So what we have here is that if you see a sphere in three space, and that induces a zero map, and if you have a torus in three space, that induces multiplication by 2. What we mean by this is that the sphere and torus are forced to be unknotted. So if you, in 4 space, if you see an unknotted sphere or torus, you know what kind of Khovanov map is induced by them, respectively. But now Tanaka and Rasmussen extended Barnatan's torus relation in particular from 3 space to what you can think of as being an almost complete lift to 4 space. So the case that they consider is where the torus is allowed to be knotted in some complicated way. So if you looked at an unknotted torus by Barnard's relation, you know that that's multiplication by 2. But what Tanaka and Rasmussen showed is that even if your torus was knotted in some complicated way in 4 space, the induced Khovanov map is still multiplication by 2. And if you had a knotted sphere that induces multiplication by 0, but this is a fact that in particular did not require any work of Tanaka or Rasmussen, but just follows by observing closely what is happening with the gradings. Okay, so Tanaka and Rasmussen's results are able to tell us what kind of Khovanov map is induced by a knotted sphere or a knotted torus in 4 space, but this still applies only to a sphere or a torus that may be knotted but viewed in isolation. That is, the sphere or tori may not be linked up with some other components in 4 space. So in order to somehow complete this lift to 4-dimensional space, we would like to know what happens when the sphere, that is, so on the rightmost column, the sphere is indicated in blue, and you may have some arbitrary cobordism indicated in red, and these may be linked up in some complicated way. In particular, this sphere is also allowed to be knotted up as well. So it wasn't already known what the Khovanov map induced by such a cobordism is, but by virtue of our main theorem, what we can do is that you can look at this blue sphere and you are able to pull it apart from the red cobordism. And what allows us to do this is that we look at the endpoints of this cobordism. So you look at this left side and then you look at the right side of this cobordism. You notice on the left side, you only have a red component, no blue components. And on the right side, you only have a red component and no blue components. So in some sense, on the two ends, the red and blue components are vacuously split from each other. And what that allows you to do is that you can just separate the red and blue components without changing the induced Khovanov map by virtue of our main theorem. And then you can apply the relation for a knotted sphere separately and then conclude that the induced map is 0. Now you can do a similar thing for a torus which might be linked with some arbitrary cobordism. And so what you do is first that you separate the blue torus from the red cobordism by applying our main theorem, because the endpoints are vacuously split, and upon doing so, you have just 2 times the red cobordism. So what this tells us is that now if you look into 4 space and you see a sphere or a torus that may be knotted but also might be linked up in some crazy way to other cobordisms, then you can blindly apply Barnard's sphere and torus relations without worrying about the knotting or the linking information. So in some sense, this completes a lift of Barnard's sphere and torus relations to 4-dimensional space. And this is the way we will be applying our main theorem towards an application. Before that, I should also say that the main theorem completely characterizes the Khovanov-Jacobson number of a closed cobordism. So the Khovanov-Jacobson number of a closed cobordism is an invariant of a closed cobordism that is obtained by looking at the Khovanov map induced by this closed cobordism when viewed as a cobordism going from the empty knot to the empty knot itself. So this is given by, this map is described by multiplication by an integer. And previously this was completely characterized by the genus for cobordisms with 1 component. But now if you have multiple components, you can sort of separate them by virtue of our main theorem and then use the known characterization for each individual component. So the main application that motivated our main theorem and that sort of led us to try and prove the main theorem is something that we will now discuss. So Zemke showed that if you have a ribbon concordance, then that induces an injective map on knot-flow homology. So ribbon concordance is a concordance with only index 0 and 1 critical points. And knot-flow homology, just like Khovanov homology, is also a link invariant that is functorial, which is to say that if you have a cobordism that induces a map between the knot-flow homology groups on either end. And after this, Levine and Zemke extended the result to Khovanov homology. That is, they showed that if you have a ribbon concordance, that induces an injective map on Khovanov homology as well. So we can think of these results as providing obstructions to knots or links from being ribbon concordant to one another. Now we'll describe a generalization of a ribbon concordance. So we say a concordance C is strongly homotopy ribbon if the complement of C can be built from S3 minus the neighborhood of K times the interval by adding 4-dimensional 1 and 2 handles only. Okay, so Miller and Zemke proved that a strongly homotopy ribbon concordance induces an injective map on knot-flow homology. So this is an extension of the statement that Zemke showed about ribbon concordances inducing an injective map on knot-flow homology. So the remaining question was whether Khovanov homology also induces an injective map on strongly homotopy ribbon concordances. And this is the statement that Adam and I showed. That is, we showed that if you have a strongly homotopy ribbon concordance, it induces an injective map on Khovanov homology. And the way we went about proving this is by making use of our main theorem. So this ends the first part of my NCNGT talk, and I hope that you will also watch the second part, in which I describe some of the tools that we use in order to prove our main theorem, as well as briefly provide a sketch of the proof of the main